Any question? If you don't have any question, let's go on. I said earlier last week, we will perform the hypothesis test regarding to population, and we are interested in comparing mu1 and mu2, the mean value of two populations. Okay, we are comparing which one is bigger, mu1 smaller or mu1 bigger, or they are equal. Okay, that's the hypothesis study. Three different sets. We are not using this. We are using this, the lower part. We are measuring their, we are interested in their difference, and we are interested in whether they are equal or not. Okay, so we turn this into this, and turn this into this, and turn this into this, and these two settings are equivalent. Okay, these two settings are equivalent, and so are these two settings. Okay, so before I go further, let's go back to the let us go back to the one parameter, one population case. Okay, here, one population, and that's a summary I made for you. That's a summary. Okay, the decision rules or the decision rules for three hypothesis study, 1, 2, 3, and that's the this is the rejection region, or called the critical region. Okay, the standardized form and the non-standardized form, and they are exactly the same. And they lead to the exactly the same decision, H1 or H0. Okay, and okay, that's the rejection region or the critical region. All right. Okay, this is the hypothesis setting. This is the test for the population mean. One parameter, one population case. There are the population normal with the first parameter mu and sigma squared, where sigma is known, right? That's the first. That's the first hypothesis set testing we have learned. Okay. But these decision rules are very unrealistic. Why? Raise your hand if you know the answer. Why unrealistic? Thank you. Why unrealistic? Because in practice, the value of sigma is often unknown. Okay, so this is useless in practice. In real world, it is useless. All right. So what can we do if the value of sigma is not known? We don't know the true one, then we can use the fake one. Okay, that's simple standard deviation. All right, and don't worry about the fake one, because by the law of large number, the fake one and the true one will be very close when n is the large. Okay, by the law of large number. All right, so that's what we can do without knowing the value. Without knowing the value of sigma. Here, you see this? We change very, the change is very. Here sigma is replaced by equal s, and z replaced by t sub -1. Where n-1 is the degree of freedom of the t distribution. Hey, attention! Okay, where sigma is unknown. Okay, and the change is very little. Okay, so where are the changes? Where are the changes? Sigma replaced by middle base, and C table replaced by D table. Okay, T is the degree of freedom -1. So all you need to do, hey, we have 6. Now we have 6 decision. 3 in the previous slide, and currently we have 3 decision. But in fact, there are only 3 to remember. But the 3 to remember can be reduced. The 3 to remember can be reduced to 1. Right? The first one here. The first one here. The 3-1 can be reduced to all you need to memorize is this one. If you can do this one, then you can do this one. When the direction change. Oh, yeah, when the direction change. Okay? Okay. What happened? Well, I made a big mistake. Sorry. I will modify this. I will correct. It's a defense. It is not correct. Sorry. I don't know what's wrong. Okay, what happened? Yeah, this is correct. Okay, all you need to memorize is the first one. If you can do this one, you can also do this one and also this one. Okay, if you can do these 3 hypothesis testing, then you can do the next 3. Okay, then you can do the next 3. Okay, right? Then you can do the next 3. 1, 2, 3. Right. Okay, so it's not 6. Actually, it's 3, or even smaller. It actually it's only 1. Okay. And okay. In some textbook, C-test is used. Okay, C-test, C is used when n is bigger than 30, right? But in exam, I will let n be smaller than 30. So that you have to use TK, right? Okay. And then let's go back. Let us go to the hypothesis testing for population proportion here. The decision rule for 3 hypothesis setting. The test of population proportion D of the Bernoulli scheme. Okay, hey, we are still in a one population case. Okay, note that here P hat is actually X bar. Okay, in fact, hey, this is X bar, right? This is X bar, and this one plays the role of multi-role in the previous slide. Okay, and this one plays what role? Raise your hand if you know the answer. What role did this one play? Yeah. Yes, the standard deviation, right? And yeah, I will give you extra clues. It plays the role of sigma in the previous slide, right? And this decision rule is constructed under the assumption of H0. H0. So what is H0? H0 assume that the value of P is P0. So the parameter here is all are also, are also are all it's all here the parameter value is the value under the null assumption, the null hypothesis. The value comes from the null hypothesis because the rejection region is constructed under the assumption of x0. So here we use the value under the assumption of n0. So it is P0 here, P0 here, P0 here. And so is that the other two formula. Okay. So and what test do we use? D or T? C. In a test of population proportion, C test is always used. Okay. Okay. This one plays the role of X bar in the previous slide, and this one plays the role of mu0 in the previous slide, and this one plays the role of sigma in the previous slide. So nothing is changed. So how many formula here? 9 formula. But in fact, they are 3 formula. Because they share this very same form. Very same form. Okay, same form as this. Okay, same form here. Same form here. Okay, same form. Okay, same form. X bar minus mu0. Next slide, so also are the next slides, next two slides. And sigma, so and so are the ones in the next slide. Okay. Okay. And Z is also used in the third slide. P, population P. The only difference is in the second slide. Here. Yeah. Where in the second slide, sigma has to be replaced by beta F, and Z has to be replaced by T when n is smaller than. Okay, so that's what I summarized. That's what I summarized for you in the one population situation. All right. And we are going to the, and now we are going to the two population case. Okay, so let us go to the two population case. Two population case here, yeah. And I will correct this part. These are all wrong. Okay, I will correct it. Here. Okay. Now we perform the hypothesis testing regarding this population. Okay. First, the population has a standard mean value B1 and a standard deviation sigma 1. Second population has mean value mu2 and a standard deviation sigma 2. And the hypothesis is about the comparison, is to compare the value of mu1 and mu2. Okay, the three settings of the hypothesis are this, and this. Okay, the difference in the direction. Okay, okay, and about we are not using this. We are using the lower part, right? Okay. And I'm using their difference, okay? And they are equivalent. The bottom part and the lower part are equivalent, okay? Any question? Yeah. Note that the test statistics of mu in a one population. If you wanted to do two population, you have to know what to do. You have to know what to do in the one population case. So that's what we do. The one population case. Okay. Look at this. This is the test statistics in one population case, right? But in two population, we need this formula, and they are exactly the same. Hey, look at this. 3 lines. 3 lines, equality sign. Okay, 3 lines. They are trivially the same. I want it to be in the square root sign. Okay, so but in the square root sign, it has to be squared. Understand? Okay. In the two population case, we when x1, x2 all the way to xn sub n1 is from the first normal population, and y1, y2 all the way to yn2 are from the second normal population, then this is what you see, what you saw in the midterm exam. Remember? X bar minus y bar has also a normal distribution with mean value mu1 minus mu2. And variance, the variance of the difference is n1 under sigma 1 squared plus n2 under sigma 2 squared. That's the variance of this is the mean of and these are the variance. This is the variance of x bar minus y bar. Okay. Any question? If you don't have any question, then I will proceed. Okay. Now next. So if we standardize, x bar minus y bar minus its mean value divided by the standard deviation, okay? Standard deviation becomes the square root of n1 under sigma 1 squared plus n2 under sigma 2 squared. All right? Hey. See this? See this? This is why I have to mention this. Hey. This term, n1 under sigma 1 squared plus n2 under sigma 2 squared. Why? You see this? Then you will know what I have to mention this. Why did I mention this? You will know. Hey, you see this? When one parameter is n square root of n sigma. But I prefer this. Now I prefer this now because when it is one population, it is n under sigma squared. But when it is two populations, then we become n1 under sigma 1 squared plus n2 sigma 2 squared. Understand? You know the reason why I prefer this notation rather than this right now. You know, because it is easier to understand. is a better expression. It is a better expression or extension or generalization. Understand? Okay. Okay. So this is for one population. When it comes to two population, you just sum them up. You just sum them up. You just sum them. Hey. Okay. When, hey, you see this? This is what we write in one population case. Okay. When it comes to two population, then all you need to do is to sum them up because there are two standard deviations. There are two variances. All you need to do is to sum them up. Understand? So the extension is easy. Once you know, if you know this, if you rewrite this into this, then you can easily extend the expression to the two population situations. Okay. It is a better expression for it is the better expression for extending to two population situation. Why? Because when it is one population, it is n under sigma square. And when it comes to two population, then you just all you need to do is to sum them up. It is to sum the two variants. Just sum. Here it is just the sum of two variances. Okay, so what happened? Hey, what happened? What happened? Ah. Hey? Hey. Is it this one? Not this one. Where is the file? Hey? Oh, this one. Yep. Hey? What happened? Ha! Yeah. So the test statistics. So the test statistic here is to standardize x bar minus 1. And here, the mean value, mu1 minus mu2 is the value under the null hypothesis, right? And this is the standard deviation of the difference, x bar minus y bar. Okay, so what is the value of the mean? Then if you want the value of the mean, you have to go to the null assumption. Okay? To look for its value. Understand? You see that? Okay. So we have similar decision rule for the three hypotheses as just like we did in the one calculation case. Do you think it's very similar? It is. Yeah. Very similar. And what happened to the mean? What happened to the mean? Because under the null assumption, mu1 minus mu2 is 0. So minus 0 means nothing. So we say that. Okay. Okay. We don't write minus 0. It means nothing, right? It's useless to write minus 0. And now, so is this one. Hey, so what happened? What happened to the mu1 minus mu2 here? What happened? Because there is a 0 value here, so we just use the 0 as mu1 minus mu as the value of mu1 minus mu2. And so is this one. Because they are all minus 0. Okay. Either you write it or you don't write it. It doesn't make any difference. So we just save it. Okay. We just leave it. Okay. Hey. It is minus 0. If you don't write it, it's the same. So why bother? Don't bother. Okay? Just say you were. Say you were. Save it. Don't write minus 0. Don't write minus 0. Simple. And it is 0. mu1 minus mu2 here because it is 0 under the null hypothesis. It is 0. And under the null hypothesis, there is also a value equals 0. So minus 0, minus 0. So we save it. We don't write minus 0 because it is the zero state. Either you write it or you don't write it. They are the same. So that's why I do write it. Whatever. Yeah, that's why I don't write it. And I have to wipe off. I have to wipe off the Chinese letters. Here minus 0 is always here. Okay. I have to wipe off. Wipe off. What happened? Hey? Hey? What happened to the circle? Hey? Ah. Okay, no circle here. Hey, wait, what circle again? Hey? Hey, what happened to the circle? Hey, what happened? Why can I not wipe you off? What if I save it as a PDF file? Is the circle still here? No more circle. Okay, no more circle. Then what happened? Okay. Yep, this one. And so here, so minus 0 is omitted. Okay, omitted. All right. Okay. And I said, like I said, this is also unrealistic. I mean, this is also unrealistic here. Why? Hi, Sophia, why is it unrealistic, the formula in a real world? What? Unknown. Yeah. This and this are both unknown. So the decision rule is unrealistic in real world. Okay. So what happened? What can we do when they are not available? When sigma 1 and sigma 2 squared are both unknown, then use x1 to replace sigma and x2 to replace sigma 2. Okay, where x1 squared is n1 minus 1 under the sum of the square of x. Okay, and x2 squared is n2 minus 1 under the sum of the square of yi. Okay, and replace z by t, okay, degree of freedom, with degree of freedom b, the minimum value of n1 minus 1 and n2 minus 1. Okay, and this is what appears in your textbook page on page 495. Okay, and the decision rules are given in the next slide. Okay, here. And this is the decision rules for the three hypotheses setting when they are both known, when they are both available. Okay, but when they are not both available, then use this. For a three hypothesis setting, the test of mu1 minus mu2, where mu1 and mu2 are calculation means of sigma 1 and mu1 sigma 1 squared and mu and mu2 sigma 2 squared respectively, where sigma 1 and sigma 2 are both unknown. And the degree of freedom is the minimum value of n1 minus 1 and n2 minus 1. Okay. Hey, it is very similar to the one population case, right? Right. Very similar to the one population situation. Hey, if you cover this, it is almost the same as what you saw in the one population situation, right? Okay, 10-minute break.
Yep, this is better. So how many formula do we have so far? I think it's 50, 1, 5 here. 3, hey, 3 here, when sigma is known, and 1 population came. And next, 3, sigma unknown. Okay. Here, sigma unknown. And the formula has the same form. The 3 formula has the same form as before. Okay, as S replaced by sigma and C replaced by sub n minus 1. And now, for the population proportion, very similar because they also have the same form as before. Okay, this is sigma, this will play the role of sigma, and this play the role of x bar, and this play the role of mu sigma. They're exactly the same, right? Exactly the same. Okay, so this is the one population case. For 2 population, before we go to the 2 population case, we needed this. We needed to rewrite this formula and put sigma into the square root as sigma squared in the square root sign. Okay, and this is one population, and when it comes to 2 populations, there will be 2 such things. The 1 sigma 1 squared plus and 2 sigma 2 squared here. And 1 sigma 1 squared and 2 sigma 2 squared. Okay. Here. Yeah. So this is the test statistics, right? And then here it is the value of mu1 minus mu2 under the mu1 hypothesis. So when they are both available, sigma 1 squared, sigma 2 squared, then this is the test statistics, right? And the formula are exactly are very similar to what we saw in the previous slide. So very similar. Hey, the direction. Hey, look at the direction. The red sign here. Direction smaller, and the direction smaller. The same. Okay. And I don't write minus 0 because it means nothing. Okay, so just leave it without minus 0. Okay, minus 0 are omitted. What happened to the
Hey, minus 0 are omitted. Is omitted. So we wipe off the minus 0 here. Okay, and these are the rejection region, right? And when the value of sigma is unknown, sigma 1, sigma 2 square are both unknown, then replace them. Express by 1 square and 2 square, right? And replace d by d with the degree of freedom. Where is the degree of freedom? Is the minimum value of n1 minus 1 and minus. And this formula appear in your textbook on page 495. So the decision rules are given in the next slide here. And you will see that the formula are very similar to the previous slide here, right? The difference is the sigma replaced by S1. Sigma 1 replaced by S1, sigma 2 replaced by S2 squared. And these replaced by T with the degree of freedom. And here the degree of freedom is the minimum value of N1 minus 1 and 2 minus 1. Okay? So this is the rejection region for free hypothesis setting, right? Any question? Any question? If you don't have any question, then I will proceed it. All right. Okay. Let's go to the let's look at some example in your textbook. The textbook example. Here. Leisure time. Leisure time example, please go to page 485. For 85, example 9-1, page 485, leisure time. Right? Two random sample. Of leisure times. Okay, per week. Spend per week. A random sample. Okay. X35. Okay, are drawn, is drawn. Now where X bar is 39.6. Okay, and another sample. Y1, Y2, all the way to what? Also 35. This is a bad example. I don't like the example because they use the same sample size. Of ages 46 to 55. Per week. Also drawn. With Y bar equal Y bar equal 35.6. assume that sigma 1 equal 6.3. And sigma 2, the second group, equal 5.8. Alpha equal 0.05. Can we conclude that there is, hey, look at the wording. There is a significant evidence difference. In the average time, each group span per week. On leisure activity. Okay, per week. Any question? And look at this. To conclude that there is a significant difference. Hey, this, hey, your setting of hypothesis, your setting of hypothesis comes from this. Should be based on this. Hey, significant difference. He says the difference. He does not want you to compare. Okay, which one is bigger and which one is small. So all you care about is the difference. So the null hypothesis is equal or not, and the alternative hypothesis not equal. Okay, so this is a this is what? This is the two-tailed test. Right, two-tailed test. Okay. This is a two-tailed test. Okay, so solution. So solution. As a null hypothesis, alternative hypothesis, mu1 minus mu2 equals 0. In this case, they are the same. And if this is true, then there is a significant difference. All right. So, and these statistics here is x bar minus y bar, right? Minus mu1 minus mu2 under the null hypothesis. It's 0 here. and divided by the square root of 35 sigma 1 square plus n2 sigma 2 square. Hey, the sample size don't have to be the same. All right. They don't have to be the same. And 1. So it is what is it? 39.6 minus 0 and 35 plus 35 under 6.3, 5.8. 6.3. Hey, don't forget to square it. So what is it? It is what is the value? 2.9. Hey, the value is very large, relatively large. Then the z value 1 point. Hey, because it is the two-tail test. So so 1.96, which is equal to z 0.05. Hey, divided by 2. Don't forget to divide it by 2. Okay, divide the level of significance by 2. Because it is the, and this is 2.9. 2.9. Okay, and so the decision is to reject the null hypothesis. So what happened? So we reject the null hypothesis in favor of the alternative hypothesis at alpha equals 0.05, right? That is, we see significant difference in the mean measure time of two groups. Okay. Any question? Okay, or we can use the p-value approach. The p-value method, right? Z equal, right, minus 0 divided by the square root of 35 plus 35 which is equal to 2.90. Okay, and the p-value is the area right to is the area right to the critical value 2.90. Equal. Let's go to the table. Hey, in the exam, you will be required to do the test by p-value as well. All right. Let's go to the table. Yeah, here. Um, 2.9. 0, 0, 19. 0, 0, 19. Okay, which is much smaller than 0.05, 0.25. So what happened? Eh? What happened to what I just wrote? Oh, something is wrong with it. Yeah, and 0.0019, which is smaller than 0.05. So reject the null hypothesis. Okay. Any question? Any question? If you don't have any question, then we will go to another example. The example where, let's look at an example where the value of the system of 1 square and 2 square are both down. That's one. Yeah. What? Demonstration to be? No, the what? Oh, sorry. Is it? It used the real sigma. It used the real sigma. Page 485. Yeah. And next example, we will use S1 and S2 because sigma 1 and sigma 2 are both on. Right? Please go to work absence. Okay. Please go to the work absences. In this example, sigma 1 and sigma 2 are both unknown. And the example number is example 9-4. Okay. X1, X2, all the way to X9. Okay, are from normal mu1 sigma 1 square and y1 y2 all the way to y7. Mu2 sigma 2 square sigma 1 and sigma 2 both unknown. Okay, are respectively the sick days, number of sick days. Men and women take. Okay, and x bar equal x bar equal 5.5. And y bar equal 4.3. And s1 square x1 equal s1 equal 1.23, s2 equal 1.90. Okay. Can it be concluded that there is a significant difference in means. Men and women. Okay. Okay, I summarize. I summarize what it is described. What is described in the textbook. The example says that there are a sample of 9 men's sick days, and a sample of 7 women's sick days. Okay, and there so that the number of sick days is normally distributed with mu1 and sigma1. Okay, for men, and the number of sick days is also normally distributed. Okay, you choose sigma squared for women, and 9 sample of 9 and sample of 7 are both true. Okay, okay, and the mean value of the sample, first sample is 5.5, and the mean value of the second sample is 4.3, and also this is also calculated from the sample because sigma 1 and sigma 2 are both on in this example. Okay, sigma 1 and sigma 2 here. So and again, and equal 0.05, and it be concluded that there is a difference between in the mean sick days of men and women. Right? You wanted to test is if there is a difference, then this is a equal or not equal. So it is a two-tailed test. Okay. Two-tailed test. So solution. The hypothesis are specified as mu1 for men and mu2 for women are equal. Mu1 not equal to mu2, but we don't like this expression. We don't like this setting. We like this alternative setting. Okay, mu1 minus mu2 equals 0. Mu1 minus mu2 not equal to 0. Okay, that's the setting of the hypothesis. Do we have any question? If you don't have any question, then I will proceed. Oh. Yep. And this time it is t. This time it is t here equal x bar minus y bar. Okay, minus 0 under the null hypothesis. And this is n1 s1 square. Sorry, s1 square plus n2 s2 square So it is 5.5 minus 4.3, right? Minus 0 divided by the square root of 9 under 1.23 plus 7 under 1.90 squared. And it is 1.972. Whoa. Yeah. The time is up. So let's finish it next week. Roll call time again. Let us make the roll call. Get yourself all ready. Hello. Hello. Yeah, here. 1 second, 2 seconds, 3 seconds, 4 seconds, 5, 6. That's it. Okay, see you next week.